So welcome to another practice problem. This is problem 7.3 out of the textbook, and it shows here for the cantilever beam and the loading, derive the equations for the shear force and bending moment for any location in the beam. It asks to place the origin at point A, and then plot the shear force and bending moment diagrams for the beam using the derived equations, right, or the derived functions. So at this point you should be familiar with being able to draw a free body diagram of a cantilever beam, showing its exterior reactions, and then taking a distributive load and condensing a distributive load down to a point load, which I've drawn here. So then we'll solve for, say, the magnitudes of our exterior reactions. We want to know what Cy is and the moment at that point. So we'll sum the forces in the y direction, which will equal 0, and we'll only have three forces: W sub A multiplied to A, W sub B multiplied to B, and then Cy. Summing the forces in the y direction, you should get Cy to equal W A multiplied to A plus WB multiplied to B. And then solving for our moment, we will sum our moments at C, which will equal 0, identify a positive direction. In doing this, you should get the moment at C to equal negative WA multiplied to A, multiplied to the entire distance, which would be B plus 1/2 of A, so B plus A over 2, minus WB multiplied to B, and then the moment arm, which would be half of B. So this is all review. We should have been able to be very familiar at this point. Now, the next thing that we want to do is the actual mechanics of materials portion, which is we are going to make an equation for our distributive load from point A all the way to C. And if you look here at point B, our loading conditions change. So we need to make an arbitrary cut somewhere here between A and B and determine a function. And then we'll make another cut between B and C and derive another equation. So between A to B, what we'll do is we'll just draw another free body diagram, right, with a distributive load on it, our shear, which in this case will be acting in a positive direction, which is down, and our moment, positive direction, which acts this way. So this is our W, since this is A heading to B, and from A to this arbitrary cut that we've made, this is just some unknown distance x, and our distributive load is going to be WA, right? So we're going to do the same thing for this free body diagram that we did a moment ago for our external reactions, right? It's pretty much the same thing. So we have our distributive load, which is magnitude is going to be W sub A. Now, if we condense that to a point load, how would we do that? Well, it's really the area of the distributive load. So the area in this case is going to be W sub A multiplied to X. So if we sum our forces in the y direction, sum our forces in the y, which equals 0, positive being up, we'll have negative shear minus our distributive load multiplied to our distance x. So then our shear equals negative W sub A x. Okay? So then we'll build a moment. So we'll sum our moments at the shear point equaling 0, identify a positive. And our sum of the moments, then we're going to have a positive moment, right? Because m is going in a positive direction. And then our distributive load is also forcing it to go in a positive direction. But our distributive load, what we're going to do is condense it to a point load, which we already did here in our shear. So it will be WA multiplied to X, and the moment arm, because a moment is a force times a distance, and W sub A multiplied to X will be our force, and multiplied to the moment arm, which is going to be half of the distance of X, so it will be X over 2 equals 0. So in this case, our moment then will equal negative W sub A X squared over 2. Okay? And so these are our answers, our intermediate answers for the distributive load from A to B. Okay? So now we're going to do another section, right? From B to C, which is going to be this cut up here if we look back at our drawing. So we did A, which was this first part, and now we're going to do B from B to C back to the end of the cantilever. So again, we'll draw a free body diagram, right? So our free body diagram then has two distributive loads on it. We'll have our distributive load acting from A to B, and then another distributive load acting from B to some unknown distance. So this is X and this is A. So our shear acts here, our moment acts here. This is W sub A, and this will be W sub B. X minus A. So the whole distance of this will be X, right? So what we'll do now is we'll sum our forces in the Y, which will equal 0. So we get negative V minus our WA multiplied to A minus W sub B multiplied to X minus A, because that would be the area here that I identified as being, or the distance, I'm sorry, the distance there of this distributed load. So that'll equal 0. And so we can say our shear for this section is going to equal negative W sub A multiplied to A minus W sub B multiplied to X minus A. And that will be the solution for the shear for section B to C, right? So the next part is we're going to sum our moments around the shear point, which is going to be what we'll do is we'll say we'll have a positive moment M plus our W sub A multiplied to A, right? Let me fix that. Multiplied to A, because that's our force, multiplied to X minus A over 2. Now why did I do that? X, because our whole moment arm is X minus half of A over 2, right? So this distance, which might be a little confusing, but what we've done here is this from here to here is A, right? And from here to here is X minus A, and our whole distance is X, right? So if I'm going to make and condense this to a point load, then the distance from here to here is going to be A over 2, right? So if I do X minus A over 2, that will give me this distance here. So this is X minus A over 2, okay? So then we'll add this to the other point load, or the distributive load, I'm sorry, as it's condensed to a point load. So it'll be WB multiplied to X minus A, which is our force, right? Now we have to multiply it to the moment arm, which is going to be our X minus A, right, divided by 2, right? The whole thing divided by 2, because it would be 1/2 of X, because 1/2 of X is going to be, I guess, the distance here, minus 1/2 of a, which will be the rest of the distance over here. Okay? And all of this equals 0. So then we can say our moment will equal negative w sub a multiplied to a, x minus a over 2 minus w sub b multiplied to x minus a, quantity squared, because there's 2 of them, and this quantity divided by 2. And so this becomes the answer for the moment from the section B to C. Now, part A has completed the problem. Part B, what it asks, is for us to plot the shear force and bending moment diagrams for the beam using the derived functions. So what we can do is draw our, just a quick line is what I like to do. Oops. Straight one. And then identify the points. So this would be A, what is it? A, B, and C. Okay. And from there, we can just use our equations that we previously derived to draw our shear and moment diagrams. So our shear, right? So we could say this is our shear equation. There's going to be another line underneath here. So for our shear, we're going to have, from the first part, right, from A to B, our shear function, right, when we look at x, if we plug in 0 for x, and we're starting our origin at A, our 0 for x, that means our shear is going to be 0. But when we plug in our distance, which in this case going from A to B, our distance is A. When we plug in the full distance when we get to B, then our moment, or our shear magnitude is going to be negative W sub A multiplied to A. And between those 2 points is just going to be a straight line. Okay? So for the shear going from B to C, right? If we look at it again, negative W sub A is a constant, right? Because if you look at this equation here, right, it's really a complicated form of something that you've seen before, which is really just y equals mx plus b, where in this case, b equals negative wa sub a, or I'm sorry, w sub a multiplied to a. So when we get to that's our starting point, and then when we plug in a value here for x, right, when x is a, then this second term goes to 0 and we're just at our starting location. But as x increases and gets to b, then b minus a, right, is going to be our x value, the total value of this distance, right, which will be here. And again, this is a linear slope, so we can just draw a straight line. And I meant to draw a straight line. Okay, and then when it gets here, it just closes back to 0. Okay, because of our reaction at C, if we go back and look at what we solved for our reactions of at C, this up here equation, this value of C, is what we should obtain when we get to the end of this shear diagram. So now let's do the moment. So our moment, looking at the first moment equation, we have a negative W sub A multiplied to x squared. So the first thing you should be thinking was, well, that's a negative parabolic, right? So we're going to follow it in the same line, right, that we were solving for at B. So at this point, we should reach, right, if we were to plug A in there, if for x value, this value here should be negative W sub A squared over 2. And that's parabolic, right? Because we start at 0, because if you plug in 0 for x, it's 0. Parabolic, it should have a nice smooth curve, which I'm clearly not doing. So but use your imagination. It should be curved, right? So we'll do the same thing for our moment equation here for the second part, going from B to C, right? So from C here, right, we should have, if we were starting here, we have a, plugging in A for this function will make this go away, but A minus 1/2 of A, right? And we should get another value here, and we do that consecutively until we get to our other value at this end is C, and you should get negative WA multiplied to A squared divided by 2 minus W sub B multiplied to B squared divided by 2 minus W sub A multiplied to AB. Okay? And this here, because there's a square in this function, this is also parabolic, but it's a little bit larger. It's a larger value, so the arc isn't going to be as pronounced. So let's see if I can do this one better. Not really. Okay. Well, that one's supposed to be curved too. Okay? And this is the final solution. So we drew our shear and moment diagrams off of the equations that we derived for this problem. Okay?